Drift velocity, I have told you. This is very important, drift velocity. So you should learn this formula. Hamza, is my voice is clear now?
Yes.
Yeah. Drift velocity. And drift velocity is nothing but, I'm just explaining once more. Earlier we have the conductor and we have connected this conductor with the battery. We have connected this conductor with the battery, and V is the potential difference. V is the potential difference, or you can say voltage of the battery. And due to this battery, an electric field is generated inside the conductor. An electric field is generated, and due to this electric field, an electric force is acted on the electron. And this electron, due to this electric force and all the phenomena, this electron will move with drift velocity from negative terminal to positive terminal. Means you can say the electron here, drift velocity. I have just explained you each and everything in the last class, but just for the revision, I am just again telling. This is a conductor. This is the electron. On this electron is moves in this direction with the drift velocity. And the formula of drift velocity is charge on electron. E is the charge on electron. E is the electric field generated or external electric field. Tau is the relaxation time divided by m. M is the mass of electron. Earlier I have written me, now I am writing m. So I am writing E is the charge on electron. This is electron, and E is the electric field. E is the electric field, and tau is the relaxation time for relax of electron, the time for which electron relax between the collision is known as relaxation time. I have already discussed, but just I am writing for your revision. M is the mass of electron. Mass of electron. Electron have charge as well as mass. Mass of electron. Mass of electron. So today's topic is the relation between the current and the drift velocity. Relation between current and drift velocity. And drift velocity. Drift velocity. Relation between the current and the drift velocity. So for this, we know that the current flows in the conductor. I am taking a cylindrical conductor here, and this cylindrical conductor have the cross section area, this cross section area. This is the conductor, and this conductor have length L. Cylindrical conductor have length L. And this A is the area of cross section. A is the area of cross section. L is length of conductor. A is the area of cross section. This area, okay, cylindrical conductor. Cross section area. And we have to find the relation between the current and the drift velocity. First, I am just finding the current. First, I am just finding the current. Okay. So see here, suppose from this cross section, delta Q amount of charge is flowing in delta T time. Delta Q amount of charge flowing in delta t time from the cross section, from the cross section. We know the current will be delta q by delta t, and we also know that inside the conductor there are electrons. Inside the conductor there are electrons, and when you apply the electric field, when you apply the electric field or connected the conductor with the battery, then in that case you can say that the electrons have the drift velocity. The electron moves with the drift velocity. What I have done here, I have just connected this conductor with the battery. See, this connect conductor with a battery, and now here is the electron, and electron is moving. Okay. Electron will move uh, this is the negative terminal, and this is the positive terminal of the battery, and the electron will move from negative to, from here the electrons are moving with the drift velocity, and velocity is equal to distance covered by the electron divided by the time taken. Speed is equal to distance upon time. So drift velocity can be written as time taken to travel from here to here, time taken from time taken to travel electron from one cross section to another is delta t. So I can write drift velocity can also be written as length of the conductor divided by delta t. Drift velocity can be written in this form also. I am saying that, see here, I am saying that delta q charge is flowing in delta t time. Delta q charge is flowing in delta t time, and velocity, or you can say the magnitude of drift velocity, can be find out by the distance covered by the electron divided by the time taken. So distance covered is the length of conductor and time taken is t, delta t. So drift velocity is this. So if, and one new term is here, one new term here is small n. Small n is the number of free electrons per unit volume of conductor. Suppose if you take a copper conductor, then you have 10 to the power 23 something like that free electrons in a unit volume. So you can say that in a conductor there are large number of free electrons, and is the number of free electron in a unit volume of the conductor, in a unit volume of conductor. And total volume of the conductor here, total volume is area into length, means AL. The volume of this conductor is area into length. So if you want to find the total number of electron, N is the total number of electrons, total number of free electrons, you can say total number of free electrons in the conductor total number of free electrons in the conductor. If I want n total number of free electron in the conductor, then number of electron per unit volume into the total volume, I will get this like in a conductor having a volume of 5 meter cube. If someone is saying in 1 meter cube there are n number of free electrons, so in 5 meter cube there are 5 n electrons. Means what you are doing? You are doing the multiplication of volume with number of electron per unit volume. So here this is the number of electron per unit volume into volume. N is the total number of electron. Now we have this number of free electron, and if we want to calculate the charge flowing, this will become NaL into E. E is the charge on electron. Suppose you have 5 electrons. You have 5 electrons. You have 5 electrons. Means you have a charge of 5 electrons. You have a charge, and charge on 1 electron is, if I am supposing, is E, then you have a charge of 5 total number of electron into charge on electron. Here NaL is the total number of electron into E is the charge on electron. Now current I is equal to delta Q divided by delta T. Now charge is NaLE divided by delta T, and this is NaE, and I can write this Ly delta T, and Ly delta T is the drift velocity. See here, Ny drift velocity is Ly delta T. So Ly delta T is the drift velocity. So current, the relation between the current and the drift velocity is this: I is equal to A N E V suffix D. So this is the relation between the current and the drift velocity. Relation between the current and the drift velocity. So we have this relation, and you should remember this relation in terms of A is the area of cross section, N is the number of electron per unit volume of the conductor. I am writing again, area of cross section, N is the number of electrons, free electrons, number of free electrons per unit volume of conductor. E is the charge on electron, magnitude of charge on electron. Vd is the drift velocity. Vd is the drift velocity of electron. Drift velocity of electron. So Hamza, please note it down. This is very simple derivation. We have a cylindrical conductor, and we have calculated that in a delta T time, delta Q charge is passing through the cross section, and after that we have calculated the current, and the drift velocity is given by the length of conductor divided by the delta T. Delta T is the time taken by the electron to complete the length of conductor. So Hamza, have you written this? Now please take the screenshot of this or note it down.
So done.
Yeah. Actually, this is na Vd is the drift speed, you will say. Means you can say this is the magnitude of drift velocity. This is not the velocity. Velocity is a vector. Magnitude of drift velocity. Return this, return.
Yes, sir.
Okay, you should write this also. Please take the screenshot or now. Done? Okay. Okay, fine. So this is the relation between the current and the drift velocity. Now we will discuss about the Ohm's law. Ohm's law. You have studied in the 10th standard Ohm's law. Ohm's law. So Ohm's law is the potential difference across the ends of the conductor is directly proportional to current the physical along with the physical quantities, and the temperature remains constant. So Ohm's law is, writing the Ohm's law, if if temperature temperature and temperature and other physical quantities, other physical quantities means you can say the small n, or the volume, or you can say length and area. If temperature and the other physical quantities physical conditions, other physical conditions are kept constant, then in a conductor, suppose this is a conductor and this conductor is connected with some battery, and the potential difference across the ends of the conductor is V, and L is the length of the conductor, E is the electric field generated in the conductor. So and I is the current flowing in the conductor. So Ohm's law tells that potential difference across the ends of conductor, across the ends, this is the potential difference across the ends of conductor. V is the potential difference or voltage across the ends of conductor is directly proportional to the current flowing in the conductor. Is directly proportional to the current flowing in the conductor. But you cannot say always potential difference is directly proportional to current. Always you cannot say. You can say only if the temperature and the other physical conditions like length, area, and the number density of electrons remain same. Then you can say the potential difference across the ends of the conductor is directly proportional to current. This is the statement of Ohm's law. This is the Ohm's law. This is not this. This is not Ohm's law. This whole is Ohm's law. You have to include this statement also along with this. Okay. So the potential difference, V is the potential difference. Potential difference is directly proportional to current, And when you remove this proportionality sign, you will get a constant V is equal to IR. You will get this. V is equal to IR. And R is the constant R is the resistance of conductor. Resistance. R is the resistance of the conductor, or you can say the wire you have taken. If I plot the graph of potential versus current, if I plot the graph of potential versus current, this graph will be the straight line passing from the origin. This is the graph between the potential. V is the potential difference. V is potential difference. Potential difference. Graph of potential difference versus current will be the straight line from this equation. V is equal to IR. The equation of straight line. The graph will be like this, the straight line. Okay, and if this the straight line is making an angle theta, then slope of this graph, slope will be equal to tan theta, and that tan theta is equal to resistance. Tan theta is equal to resistance. So you can say V versus I graph is a straight line. V versus I graph is a straight line. Sorry. So the V versus I graph is a straight line. So this is the Ohm's law. Now we will discuss about the resistance. What is the resistance? We will discuss. Resistance. We are familiar with resistance. In 10th class also we have studied. So resistance is the obstruction in the path of current flow. This is the resistance is the obstruction. Obstruction, you can say hindrance. Obstruction offered by the any material in the flow of current. The resistance will try to oppose the flow of current. And resistance is given by the potential difference divided by the current. R is equal to V divided by I. I is current. This is the scalar quantity and the unit is SI unit is ohm. OHM ohm. And you can also write the unit from here. This is unit of potential difference is voltage, means volts, and this is ampere. Volt per ampere is ohm, or this ohm is sometimes represented like this. Or you can say this is written as this. This is a symbol of ohm. Sorry. Okay, so this is the resistance, is the obstruction offered by the any material in the flow of current. And why the resistance is there in the wire is cause of resistance. We have discussed earlier that electron collides with the ions inside the conductor when the electric field is applied, or on the across the ends of the conductor there is a electric force on the electron in the opposite direction of electric field. Then the electron collides with the ions in the path, positively charged ions in the path of it. Due to that, the momentum of electron changes. The momentum of electron changes, and due to the change in that momentum of electrons, means you can say due to that collision, the speed of electron, or you can say the velocity of electron decreases, and this is due to this the flow of current decreases. So cause of and resistance. So the cause of resistance is just simply, you can say, the collision of electrons with ions. Responsible for resistance. You can imagine a conductor where there are no ions. There will be no collision. There will be no collision. There will be no resistance. If there is, if the collision is happening, what is happening with the when the collision takes place? The momentum of electron changes. Means the direction of motion of electron changes. Earlier, the electron is going from the negative terminal to positive terminal in this direction, from the negative to positive. Now, after the collision, there is an interruption in the motion in the motion of electron. Due to this, the current will decrease. Or you can say, in the same way, you can say, due to this, the resistance, a term resistance is produced. Actually, resistance is the hindrance. So now you have seen the resistance is R equal to V by I. Now we will write the resistance in some different form. resistance in microscopic form. Microscopic form. Microscopic form means in terms of mass, length, area, charge on electron, and relaxation time. We have just discussed that current is equal to A and charge on electron into drift velocity. I have just discussed this. From here, I can write, see here, we have derived this relation earlier. I is equal to A NE VD. VD is the drift velocity. So A and E, drift velocity is charge on electron, electric field, relaxation time divided by mass of electron. So from here I can write I is equal to A N E square, A N E square tau by m into electric field. And in a conductor, please remember this point, in a conductor, the battery is connected. If V is the potential difference across the ends of conductor, this is a positive end of the conductor, and electric field is generated, and L is the length of conductor, then electric field can be written as potential difference divided by length. So I is equal to A N E square tau by m. Electric field is potential difference divided by length. So from here I am writing I divided by V is equal to ANE square tau divided by ml. But the resistance we know is potential difference by current. Now reverse this. Take the inverse of this. V by I. So ml will in the numerator and ANE square tau in the denominator, and this is the resistance. So resistance can also be written in this form. We can also write the resistance in this form in terms of mass, length, area. N is the number of free electron per unit volume. N is the number of free electrons per unit volume of conductor, per unit volume. Tau is the relaxation time. Tau is the relaxation time. And E is the charge on electron, A is the area, L is the length, M is the mass of electron. Mass of E is the magnitude of charge on electron. Charge on electron is negative. I am taking just charge on electron. We will talk about the L, and L is the length of the conductor. Sorry. So you have this resistance is equal to ml divided by ne square, ane square. So from here you can say mass of electron and charge on electron will be constant. The mass and charge of electron will never change. The mass of the electron or the charge of the electron will only be changed when the speeds or the velocities is comparable to the speed of light. That is the different part. But here in the current electricity, mass and charge of electron will be constant. So we can say the resistance is directly proportional to L from this formula. This formula is very important. So I can say, number one, this resistance M is constant. Resistance is directly proportional to length. Secondly, resistance is inversely proportional to area. Thirdly, I can say resistance is inversely proportional to 1 upon small n, and remember that this small n is the property of material. If you change the material, this n will change. Property of material. You can write this depends upon material. N depends on material. If you change the material, then N will change. For copper, N will be different. For aluminium, N will be different. Fourth is, from here you can see you can see resistance is inversely proportional to relaxation time. This charge of electron will remain constant. So resistance is inversely proportional to the relaxation time, and relaxation time is a function of temperature. Depends on, I have told you earlier, how the relaxation time will depend on the temperature. Earlier I have told you that relaxation time is the time for which the electron is relaxing, not colliding with the ion. Suppose you have increased the temperature. Now the collision of electron will become fast, and the relaxation time for relax of electron will decrease. If you increase the temperature, tau will decrease, because the time for relax of electron will decrease. Sorry. Tau is the relaxation time. So now Hamza, please note it down. From where do you want to note? From here, na? Hamza, please note it down. Completed, Hamza? Hamza, are you there? You can write in the chat box. Hamza, are you there or not? Please respond.
Yes, sir, I'm there.
You are there, so you can tell me now. So have you completed this or not? You have completed this resistance in microscopic form. You have completed this. Your voice is not coming to me. If you are getting problem in speaking, then you can write in the chat box.
Okay, sir, I'm writing inshallah.
Yeah. Have you please tell me, have you come from where you want to write? You have done completely all the things still here. Means uh, just a minute, just a minute. Okay, fine, fine, fine. This thing completed. This thing. Oh, okay, 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 okay. Very good. Okay. But you should have the notes. But you and also arrange the notes in a proper manner. So next thing is the resistivity. Next thing is the resistivity. Next thing is the resistivity. And this resistivity is the property of material again. This is independent of area and length, area of cross section and length of the conductor. Area and length. We know that resistance is directly proportional to length and resistance is inversely proportional to area. So resistance is, I can write like this. So here when you remove this proportionality sign, you will get a constant, and that constant is known as resistivity, rho. Resistivity is rho, rho, rho. R is equal to, so resistance can also be written in this form. Resistance we can write resistance in this form. Now apply the formula of resistance here. Put the value of R. We have R is equal to ml divided by a n e square into tau. This is rho L by A. So from here we can find the rho in terms of mass and relaxation time. Okay. This L and this L is cancel out. This A and this A is cancel out. Actually, this is not working properly. So here you have, when you will calculate rho, then you have m upon n e square tau. M upon n e square into tau. So rho can be written in this form also. So see here, rho, this rho is independent of, there is no area and length in the expression of rho. So this rho is independent of length and area, independent of length and area. So SI unit of resistivity is ohm meter. If you want to define the resistivity, then we know R is equal to rho L divided by A. We know R, R is equal to rho L divided by A. If you have taken length is equal to 1 meter square, sorry, length is equal to 1 meter and area is 1 meter square. And area is taken as 1 meter square, then you will put the value here R rho, L is 1, A is 1, then resistance is equal to rho, or you can write rho is equal to resistance. So resistivity is the resistance of unit area and unit length, wire of unit area and unit length. So I am writing for the definition of resistivity, you can write resistivity is resistance resistivity is resistance of conductor. Resistivity is resistance of conductor having unit area and unit length. Length of unit area and unit length. Okay. This resistivity, it depends only on the nature of material, and the temperature. And temperature. See here, m is equal to, sorry, rho is equal to m upon ne square. M upon, this is not working properly. That's why I'm getting problem here. So for the resistivity, we have formula rho is equal to m upon ne square tau. Rho is equal to m upon ne square into tau. So see here, mass of electron is constant, charge on electron is constant. So rho is inversely proportional to n. So means it depends on the nature of material. Rho n depends on the nature of material, and tau depends on the temperature of the material. So we can say resistivity depends on the nature and the temperature of the material, and the temperature of the material. Take the screenshot. So now the another term is conductivity. Not conductivity, conductance. So conductance is the inverse of resistance. Inverse of resistance. Conductance is represented by capital G. Capital G is equal to 1 upon R. Or you can write, we know R is equal to ml divided by A and E square into tau. So 1 upon R you can write G is equal to 1 upon R, you can write A and E square, tau divided by ml. SI unit is ohm inverse. Another term is conductivity. Another term is conductivity. So conductivity is represented by sigma. We have discussed the surface charge density, that is also sigma. So conductivity is 1 upon resistivity, and you can write resistivity as Ne square tau by m, inverse of, you can write conductivity inverse of resistivity, and SI unit is ohm inverse, meter inverse. So this is the conductivity, inverse of resistivity. Now we have the mobility, and mobility is represented by mu. Mobility is the drift velocity divided by electric field. We know drift velocity E tau divided by mass of electron into E. E and E is cancel out from here. So you can write mobility is E tau divided by M. E tau divided by M. This is mobility. And SI unit of this you can calculate meter per second divided by unit of electric field. Now there is another term known as current density. We have current, now we have current density. Current density, this is represented by J, and current density is equal to current divided by area. Suppose this is the conductor here, and this is the cross section area of the conductor, and from this conductor this current is flowing, I is current flowing, and this is the area of cross section. Then you can write J is equal to I by A, and from here you can write I is equal to J into A. And this current density can be uniform or can be non-uniform. If this current density J is non-uniform, non-uniform means current density is same throughout the area. Non-uniform means the current density is changing throughout the area, means with the distance with respect to area. As we are moving from here to here, the current density is changing, means current density is non-uniform. If current density is same, means this will not change along the length or the cross section area. If J is non-uniform, then you can calculate the current with the help of integration. And one thing more, this current density is a vector quantity. Current density, but usually in NCERT, or you can write it is vector, and direction is same. Same as that of current. As that of current. Note one point. But in NCERT of 12th class, usually the current density is uniform.
So what does that mean?
What?
So what does that mean?
Actually, your voice is not clear, Hamza. What are you saying? Okay. This term. Oh, okay. Very good. First time you asked the doubt. Current density is uniform means. Current density is uniform means. Suppose you are moving from here to here. Suppose this is a conductor. Suppose this is the conductor. Suppose this is the conductor, and you are here right now, and at this cross section you have calculated the current density. You will find the current density is J. Now you have calculated the current density here. current flowing through this cross section divided by the area of cross section here. Here is also J. Here is also J. But it can also be possible that if you have measured the current density, here is J1, here is J2, here is J3, means along the length or with respect to the cross section, the current density is changing. So this is known as non-uniform. This is known as the non-uniform. If the current density is uniform, then this J1, J2, J3 are equal. Means from here to here, the current density will not change. Got my point, Hamza? Please write in the chat box if you have understood. Getting how the current density is uniform? What is the meaning of that? You know the density is equal to mass upon volume. So if the material is same, then density generally remains same. Density does not change with respect to space in the material. Density is equal to mass upon volume. Similarly, here is the current density of current. So density of current can change within the conductor or can remain same within the conductor depending upon the situation. Hamza, getting or not?
Yes, sir. Yes, sir.
Okay. Uniform means same. Uniform means not changing with respect to distance. Usually the current density is just similarly you can say that there is a density, mass upon volume density, there is a current density. In a unit area, the amount of current is the current density. Usually the current density J is same in NCERT. And SI unit is, and this is a vector, and this the SI unit of this is, the unit of current is J is I divided by A. Unit of current is ampere, and unit of area is meter square. So you can write ampere meter minus 2. This is the unit, SI unit. Please take the screenshot of current density. This also. Taken the screenshots? Okay. Now there is microscopic form of Ohm's law. Microscopic form of Ohm's law. And simply this is in terms of current density sigma into electric field. This is the microscopic form of, this is also the Ohm's law. And here J is the current density, E is the electric field, sigma is the, I have told you, the conductivity. So this is just the you can say equivalent of current. This is the equivalent of, you can say, resistance. And electric field is, you can say, equivalent of voltage or potential difference. So you can relate this law as the Ohm's. In Ohm's law, we have current, resistance, and voltage, or you can say current, resistance, or potential difference. Here, instead of current, I have written current density, sigma is the conductivity, and E is the electric field, J is the current density. Sigma is the conductivity, and electric E is the electric field. So you can relate this. Okay. Okay, so you should remember like this formula. I am not driving this. So please take the screenshot of this. Now we will solve a question. After this, we will solve a question. And the question is, if the length of the conductor, if the length of the conductor is increased by 2%, increased by 2%, calculate the percentage change, calculate the percentage change in the resistance so initially please read the question. Length of the conductor is increased by 2%. So I am supposing we have a conductor. This conductor we have. This conductor have length L initially and area of cross section as A, and rho is the resistivity. Of this conductor. So we have formula R is equal to rho L divided by A. This is the R initial. Initial resistance is equal to rho L divided by A. Simple. This is equation 1. Now they are saying that the length of the conductor is increased by 2%. Length increased by 2% means final length L suffix F is equal to final length will initial length plus L by 100 into 2. Okay, this is the percentage, this is the change in the length. This is the change in the length. L will become this 2 by 100 into L, and when you will calculate this will become L plus 0.02 times L. This will become, when you will take L common, this will become 1 plus 0.02. This will become 1.02 L. So final length is this. We have to find now what is the final area. So suppose this is the conductor. If you are stretching this wire, suppose this is a wire or a conductor, you are stretching this wire. So if you will increase the length, then the area of cross section will decrease. Area of cross section will decrease, but the volume remains same. Volume of conductor remains same. Volume of conductor or wire will, there will no change in the volume. If you are increasing or decreasing, the length will remain same. So volume initial is equal to volume final. Volume initial means area initial A, length initial, volume final, area final, length final. This is same. This is AL. We have to find final area, and final length is 1.02 L. So L and L cancel out. So final area will become A divided by 1.02. So this is the final area. So now we can write the final resistance. We can write the final resistance. Length is increasing by 2%. Here you can see this. We have the same conductor. Now the length becomes 1.02 times of L. And there is some area, final area, and that is equal to A divided by 1.02. So for this, and resistivity will remain same. Resistivity will remain same because resistivity, I have told you, does not depends on the area and the length. I have already discussed this for the resistivity. See here, it depends only on the nature and material of the temperature, and I have written independent of area and length. Resistivity. So resistivity is independent of area and length. So we have the formula. Resistivity rho will remain same. L final minus, divided by area final. This is rho. L final is 1.02 times of L divided by area final is A divided by 1.02. So here, from here, the resistance will become rho into L by A, and when you will multiply this will become 1.02 square. So percentage change in resistance is equal to final resistance minus initial resistance divided by the initial resistance. Okay. So you can write final resistance. Final resistance is this rho L by A into 1.02 square minus initial resistance is rho L by A, and upon initial resistance, that is rho L by A. This is not P, this is rho, and multiplied by 100 also. Multiplied by 100 also. So, multiplied by 100 also. So when you will multiply this, into 100, this will become percentage change in resistance. This will become percentage changes resistance, and this will become this, and you will multiply here also with 100. Here also you will multiply 100. So now see here, this term, this term, this term, and this term is cancelled out from all the terms. So percentage change in the resistance will be 1.02 square minus 1 divided by 1 into 100, and when you will calculate, the answer will come out to be 4.04%. 4.04%. Please take the screenshots or please note it down. So here the volume will remain same. In this case, the volume will remain same. Take the screenshot. And Hamza, in the next class, there will be a test of 15 to 20 minutes of the previous chapter capacitance.
Yes, sir.
There, in the next class, there will be a test of 15 to 20 minutes, and I will give 3 to 4 questions, but short questions, and you have to write the answers. And the name of the chapter for test is capacitance only. So I want that you should revise that chapter. Okay. So
Yes, sir.
have you? Okay, Hamza. So have you taken the screenshots of this? Taken?
Yes, sir.
Okay. So let me tell you what I have told you in that chapter. Hmm. From here, from here, you have to revise. and I am just revising with you also. Okay, I'm just taking a 10 or 15 minutes. So I have, from here you have to prepare. Okay. So capacitance, I have told you the capacitance. Capacitance is the capacity to hold the charge, and and I have after that we have calculated the capacitance of conducting sphere. C is equal to 4 pi epsilon naught R. Capacity of earth is this. After that we have a topic, capacitor. So capacitor is simply two conductors of opposite charge separated by some medium. Symbol is this, and after that we have three types of capacitors, and we have just discussed only parallel plate capacitor. Spherical and cylindrical are not the part of our syllabus, so I have just discussed the parallel plate capacitor. So parallel plate capacitor are just simply two parallel plates separated by some medium. Here air is the medium, and you will get the capacitance epsilon naught A divided by distance between the plates. After that I have filled the dielectric completely in between the plates, and I got this formula, K epsilon naught A divided by D. K is the dielectric constant. After that, this I have filled the dielectric partially, and we will get this formula. And this formula is not that important, but this formula is important. And test, we have taken that, we have done the test also there. And after that we have introduced in between the plates of capacitor a conducting slab partially, and we have done some questions also, and numericals. These types of questions you should prepare. And after that, energy is stored in a parallel plate capacitor. The derivation is not the part of your syllabus, so you should remember only these three formulas: U is equal to Q square by 2C, U is equal to half CV square, U is equal to half QV, where Q is a charge, V is a potential difference. Energy density, for the energy density you have half epsilon naught into E square. And there is the topic that force between plates of capacitor, and I have told you, in between the plates of capacitor the total electric field due to the both the plates is sigma by epsilon naught. If we have the electric field, we can calculate the electric force. We have done some numericals also. We have introduced the dielectric and removed the battery and all that. And one thing, please remember one thing: if uh, you are if the battery remains connected, if the battery remains connected to the capacitor, then the potential difference across the capacitor will be same always. And when you remove the battery, then charge will remain same. Okay, when you will remove the battery, then charge will remain same. And when the battery is connected, then the potential difference will remain same. Please remember this point. And if you introduce a dielectric, then the capacitance will increase K times. So we have done this in details. And after that we have series and parallel combination of capacitors. I have told you the charge will divide due to the branching. Here charge is same as there are no branching, no other wire. Here also the charge is same as the wire is same. Here now there are two branches, there are two different wires, so charge will different, and the voltage will does not change with respect to branching. The voltage will change, voltage will drop when in the path of the there are capacitors or resistors. So series combination of in series combination, the capacitors are connected like this. The capacitors are connected like this. So you can see here the charge across every capacitor is same, but the potential difference across every capacitor is different. And we have got the formula for calculating the equivalent capacitance is equal to 1 upon C1 plus 1 upon C2 plus and so on. And I have told you a special case, when two capacitors are connected in series, then C equivalent is equal to C1 C2 divided by C1 plus C2. This formula helps us to save the time. And after that we have calculated some terms: energy, voltage, charge, potential difference and all that. Now we have the, after that we have parallel combination of capacitor. In parallel combination of capacitor, across every capacitor, the potential difference is same. Potential difference is same, and the equivalent capacitance is the sum of the capacitance, like this, C1 plus C2. And after that, we have calculated the, and we have solved these questions. Actually, you should only revise the notes, then I think that will be sufficient for you. Revise the notes but properly. Here you can see this is the question we have solved. And after that, we have a topic that this is a parallel plate capacitor, and now in half of the area we have placed a dielectric of constant K1, and in another half area we have placed a dielectric of constant K2. And accordingly, we have, as this is a parallel combination, because positive plate is connected to the positive plate. See here, here the positive plate is connected to positive plate, negative plate is connected to negative plate. Here positive plate is connected to positive plate, negative plate is connected to negative plate. Then this is the parallel combination, and for parallel combination we have calculated the capacitance, and equivalent capacitance is come out to be epsilon naught A divided by 2D K1 plus K2. Now we have introduced or filled the dielectric with respect to distance. In half of the distance we have a dielectric of constant K1. In half of the distance here we have a dielectric of constant K2. So this is the parallel combination. How this is a parallel combination? Because here negative, this is the negative plate, this is the charge due to induction, this is a charge due to induction, and this is the negative plate of the capacitor. Now this becomes one capacitor, this becomes one capacitor. Here the negative plate of the capacitor is connected with the positive plate. See here, negative plate is connected with positive plate, means in the series combination negative plate is connected with the positive plate. So that's so we can say this is a series combination. So for the series combination we have calculated the equivalent capacitance, and you can also say that, you can also identify this. I have written also. I have I think if area divides, then capacitors connected in parallel. Here dielectric divided into the areas. So this is a parallel combination. Area divide, then capacitor connected in parallel. If the distance divides, then you can say separation. If separation divide, then the capacitor connected in series. Here dielectric is filled with respect to distances, with respect to the distance between the plate. Then this is the series combination. Two ways to identify the things. Okay, Hamza. So in the next class, that we will have a test. Okay, Hamza. Are you there, Hamza? Hamza?